It's a great pleasure to welcome Professor Vidya Madhavan, who is Professor of Engineering at the University of Illinois at Urbana-Champaign. Professor Madhavan received her bachelor's degree in metallurgical engineering in '91 from the Indian Institute of Technology in Chennai, and then a Master of Technology in Solid-State Materials from the Indian Institute of Technology in New Delhi. She obtained her PhD from Boston University in 2000, and then followed by a postdoctoral appointment at UC Berkeley. She joined the physics faculty at Boston College in 2002, and then finally joined the faculty at Illinois in 2014 as full professor. So Vidya uses scanning tunneling microscopy and spectroscopy to investigate fundamental problems in quantum materials, where interactions between spin charge and structural degrees of freedom lead to emergent phenomena. And today she will be talking about creating and measuring the elusive Majorana Fermions. Okay, and with this, yeah, please start whenever you're ready.
Okay, thank you. It's actually a real pleasure to be giving this talk. I'm happy to be talking to this audience. I'm really sad that I'm not there, but I hope we'll get an opportunity another time for me to visit in person. So today I would like to talk about how we can create Majorana fermions and also measure them. I'd like to start by describing why these are interesting particles in the first place. And then I want you to give a brief sort of overview about under what conditions you can realize these Majorana fermions. And then I would like to go on to describe one particular system where we have, I hope I can show you that we have evidence that we can actually see these Majorana particles both as bound states as well as propagating modes. So this work was done by my former postdoc, Zhenyu Wang, with the help of my graduate student, George Oliveras Rodriguez. We have beautiful single crystals of the material that I'm going to talk to you about, which is iron selenium tellurium from Genda Gu in Brookhaven National Lab. And we have a lot of theory help from Taylor Hughes as well as Dirk Moore. So it was in 1937 that Ettore Majorana postulated the existence of these kinds of particles. A Majorana fermion, which is named after him, is a particle that is its own antiparticle. These are fermions that behave in this way. So they're necessarily neutral spin half objects. And when Majorana postulated the existence of these particles, since then for a long time we have been searching for them, because he was actually suggesting that we could find such particles as elementary particles in our universe. However, so far no elementary Majorana particles have been found, except perhaps the neutrino. And there are a lot of experiments that are being designed as we speak now to determine whether or not the neutrino is a Majorana mode. Over the last 20 years, however, we've realized that these exotic Majorana fermions can be realized as quasiparticle excitations in solid state systems. So just as a quick example, if you take a nanowire with very strong spin orbit coupling, and then you place it on a superconductor in a magnetic field, the theoretical prediction is that at the ends of the nanowire, you will find a pair of Majorana bound states. So these Majorana bound states, each Majorana particle is half of an electron and is formed as a quasiparticle excitation inside this nanowire. So why are we so interested in Majorana modes? There's a lot of interest in them for fundamental reasons. Majorana fermions are non-abelian anyons, That means that unlike fermions and bosons, where exchanging two particles can give you either a positive or a negative sign, in the case of Majorana fermions, you can get a phase, but not only that, and now I'm talking about two dimensions, when you circulate one Majorana fermion around another, you can get into an entirely different state. So exchanging two Majorana fermions actually is completely different from exchanging fermions or bosons. They're interesting, of course, to realize in solid state systems because since they haven't been observed in nature, it gives us an opportunity to actually study these exotic particles. They're also interesting because they're potentially useful as qubits in quantum computers. One of the biggest reasons that they're interesting as qubits is because they are extremely robust. In many cases, the existence of these kinds of Majorana fermions is actually protected by the topology of the system. So it's really difficult to destroy them. So this, for example, is you have two nanowires with four Majorana fermions at the end, and you can perform operations by exchanging these Majorana fermions. And these kinds of exchange operations, this is what gives you the operations required for a qubit in a quantum computer. Of course, once we're interested in these particles, and the real question is, what are the important conditions necessary to realize such Majorana fermions? And that's what I want to talk to you for the next couple of slides. So, like I said before, a Majorana fermion is a particle that is its own antiparticle. That means that the creation operator and the annihilation operator for this particle and antiparticle are identical. Now, if you just look at this, you immediately realize that one of the conditions is that you should have particle-hole symmetry. And that means that a natural place to realize these Majorana fermions would be in a superconductor. So let's just look at a superconductor. If you have a normal spin singlet superconductor, then we know that the excitations of such a superconductor are Bogoliubov quasiparticles, which are actually superpositions of particles and holes. So here are the creation and annihilation operators for the Bogoliubov quasiparticles. And you can see that each of these operators is a superposition of an electron and a hole. And the VK and the UK just give you the relative weight of the particle and the hole in this Bogoliubov quasiparticle excitation. Now, if you want, let's say you took a random superconductor and you asked the following question. In this random superconductor, how can you satisfy this condition to realize a Majorana fermion? Let's see what happens if you set these two operators equal to one another. For these two to be equal, the first condition that has to be satisfied is that UK and VK have to be identical. This means that the particle component and the whole component of this Bogoliubov excitation have to be the same. This can be realized in a real material if you have particle-hole symmetry in the normal state band structure, for example. But there's another big problem when you try to set these to be equal, which is that if you look carefully, this is a spin down operator and this is a spin up operator. So for these two to be equal, it's impossible because the spins are flipped. So the way you can realize true Majorana fermions in a superconductor is to realize a superconductor where the spin degree of freedom is not an independent degree of freedom. So either you remove the spin, so that's what I'm going to show you. I'm going to show you different ways to get rid of the spin degree of freedom. And once you're able to get rid of the spin degree of freedom, you can naturally create Majorana excitations in a variety of superconductors. So let me give you examples of three different platforms. By the way, I forgot to mention this. Please interrupt me if you have questions. I'm not able to look at the chat. So if someone puts a question in chat, Bent, would you be able to ask me the question?
Sure, no problem. Yeah.
Okay. All right. And please, yeah, I'm happy to be interrupted. Okay, so like I said, I just want to discuss three possible platforms for realizing these Majorana fermions. One easy to imagine platform is to use a spin triplet superconductor. So typically in singlet superconductors, Cooper pairs are made up of electrons with opposite spins. And in triplet superconductors, they have their same spin Cooper pairs. And so you can imagine that if you had such a spin triplet superconductor, then you've gotten rid of this problem of the spins being flipped. And in fact, sorry about that. In fact, the Bogoliubov excitations or the low energy excitations of triplet superconductors are actually, they look exactly like Majorana fermions. But the problem with triplet superconductors is, of course, that there aren't that many in nature. So nature hasn't been kind. So in fact, we know very few spin triplet superconductors. And if you want chiral Majorana fermions, then in fact, you have to also break time reversal symmetry. And so that leads you to requiring a sort of a very special topological superconductor. And it's only in these topological superconductors that you can get chiral Majorana fermions, which might be useful for quantum computation. So since nature has not been kind, we need to find different ways to engineer systems where you can realize Majorana modes. And one such system is the one I mentioned before. So now what you want to do is you want to take a strong spin orbit coupled material, which is a semiconducting nanowire like indium antimony, for example. So in such a strong spin orbit coupled nanowire, the band structure would be, because of spin orbit coupling, you would have Rashba splitting. So that's what these dotted lines are showing. These are the two bands that you would normally have split by the Rashba coupling, okay? And now if you could sort of turn on a magnetic field or introduce some magnetism in the system, you would open up a gap exactly here where these, you break time reversal symmetry, so that can open up a gap here. And once you've opened up a gap, if you can place the Fermi energy inside the gap, so the gap system is shown by the dark black lines. If you could place the Fermi energy inside the gap, then you're in a situation where you have just one band crossing the Fermi energy. And this band is very special because due to strong spin orbit coupling, you have spin momentum blocking. And due to the spin momentum blocking, basically you've eliminated spin as an independent quantum number, because once you know the momentum, the spin is exactly determined. So you can take such a system, which is a strong spin orbit coupled nanowire with some ability to gate the Fermi energy into this gap, and then put it on top of an S-wave superconductor. And if you do this, then at the ends of this nanowire, you expect to see Majorana fermions. Yes, this is really involved, but this is another way to get Majorana bound states. And then the third way is to use a topological insulator. Now, you've probably heard many talks on topological insulators, so I don't want to get into great detail about these materials, but we do know that, we now know that if you have an insulator where the bulk has non-trivial topology, then that topology, non-trivial topology, dictates the existence of these two-dimensional surface states, which have very unique properties. The unique properties are Dirac dispersion, spin momentum locking, and so on. And the Dirac crossing is protected by some kind of symmetry, like time reversal or some crystalline symmetry. So just to show you why a topological insulator is interesting, this is the band structure of the surface state, the two-dimensional surface state of a topological insulator. And this is the Rashba split state that I was talking about earlier. The difference between a topological insulator and a Rashba split band is that at any given energy for a topological insulator, you have only one set of one band crossing that energy, Whereas for a Rashba system, you have these two branches that cross at any given energy. And so a topological insulator is, it has strong spin momentum locking, just like we need. And it has you've gotten rid of the other band because of the topology of the bulk of the system. So this is an ideal sort of system to realize Majorana modes. So how do you take a topological insulator and turn it into a system where you can see Majorana modes? That question was answered by Charlie Kane and Liang Fu in 2008. They showed theoretically that there are two circumstances in which you can realize Majorana modes in a topological insulator. And they both involve proximatizing the topological insulator with a superconductor. That's not very surprising given what I told you earlier. So let's say you proximatize a topological insulator with a superconductor. What that really means is that you take a topological insulator and you put it on top of a superconductor such that the topological insulator becomes superconducting by proximity effect. So if you can do that, then what they showed is that if you turn on a magnetic field, then inside the vortex cores of the system, you will realize zero bias Majorana bound states. So that's one scenario where you can get a Majorana bound states. They also showed that if you take the same topological insulator and you somehow engineered the system such that you have two superconductors with some kind of a phase shift in the superconducting order parameter. It doesn't have to be pi, but pi is very nice. So supposing you have two superconductors with a phase shift, then at the boundary between these two superconductors, you can get propagating Majorana fermions. Now, these are Majorana fermions that can actually move. So these are two scenarios where you can use a topological insulator and realize either bound states or propagating Majorana fermions. Any questions so far? Okay.
There's none in the chat, but maybe I can ask a quick one. So how does the physics change when I now look at a 2D topological insulator versus a 3D topological insulator?
So for a 3D topological insulator, you have surface states that have Dirac dispersion. So when you proximatize a 3D topological insulator, the surface states get proximatized and become superconducting. And typically you want to proximatize it with an S-wave superconductor. And they develop a gap, the surface states. And then when you apply a magnetic field inside the vortex cores, you can see these Majorana bound states. However, in a two-dimensional topological insulator, like a quantum spin Hall system, the bulk is two-dimensional. So the topological modes live on the edges of these two-dimensional topological insulator. So the edge would be either the boundary of the material itself or the boundary of some island within the material. Now in that scenario, you can't have vortices because now the proximatized state is only it's a one-dimensional state, right? So the idea of having vortex core Majorana bound states, you can't do that. However, you can show that you can still proximatize it with a superconductor. And if you can have phase shifts or some kind of magnetism, for example, so if you're able to have different magnetic domains, you can still get bound Majorana bound states at the edges of the magnetic domain. So it's sort of a different geometry, that's all.
Okay, thanks. Thanks, Vidya.
Okay, so let's ask the question, what is the signature of such Majorana bound states? So if you did this experiment and you had the superconductor topological insulator turn on a magnetic field, the vortex core states should show up as zero bias peaks. So what I'm showing here is STM spectra. These are just density of states plots. So this is a line cut along a vortex core. And you can see far away, you see the superconducting gap. But at the core, inside the core of the vortex, the signature would be, at least in theory, a sharp peak in the density of states exactly at zero bias. Okay. What about these dispersing Majorana modes? So if you could engineer such a system, what you expect to see is you expect to see states inside the superconducting gap that live only along this edge. So that would be the signature. Okay, so this is sort of, again, a complex system with complex geometry. And because of this complexity for a long time, it was really difficult to study these kinds of systems with the STM, although some people have been able to grow films and proximatize topological insulators and study the vortex core states and so on. However, in 2015, we discovered that this material, iron selenium tellurium, is actually an ideal system to realize Majorana modes, mainly because what was shown in theory is that this material, which we know as a superconductor, also has band inversion. So one of the most important criteria to get a topologically non-trivial bulk is that you must have band inversion, meaning that at an odd number of points inside the Brillouin zone, the band structure should be flipped. So what they were able to show theoretically is that in this system, FESCTE, at the gamma point in the Brillouin zone, you have one of the bands being inverted. So because of the band inversion, the bulk of the material is topologically non-trivial, and therefore this material hosts surface states. And like I said before, it's also an intrinsic S-wave superconductor. So because you have an S-wave superconductor with non-trivial surface states living on the boundaries of the system, it's a beautiful material. It's like a 2-in-1 material. You don't have to do any engineering. And if you turn on a magnetic field in the system, what you should hope to see are Majorana bound states in the vortex cores. So now let me turn to the experiments that have been done in this material. What I'd like to show you after I describe the system and so on is the two kinds of experiments that have been done. One is where people have turned on, including us, a magnetic field and looked at the vortex core states. And the other is an experiment we did recently where we were able to find domains of superconductivity with a phase shift between two sides. And I'd like to show you what happens at the boundary of those systems. So let me start by describing the system. Yes?
Just one question. So there was actually a question from the chat as you asked me to interrupt.
Okay, sure, absolutely.
So Radha is asking, since Majoranas always come in pairs, does it mean that when we observe Majoranas in a proximatized TI, will the Majoranas in the vortices be in even numbers?
Yes. So one thing I have to say is, remember a vortex, I don't know if you could see me, I hope you can. A vortex is a vertical object and it has an end. It has two ends. And so the two ends are expected to host a Majorana each. That's the pair we're talking about. If that's not possible, then yes, you must always have two vortices in a material. So somehow you must have pairs of Majorana fermions. That's absolutely, either they live at the ends of the vortices or by some other mechanism, you must have pairs. You're absolutely right.
Thanks.
Okay. So this is FESCTE. This is the phase diagram. This is the FETE end of things. This is the iron selenium end of things. Iron selenium, by the way, is a very famous superconductor because if you make a monolayer of it, its transition temperature goes from, let's say, 11 or 12 Kelvin all the way to 80 Kelvin. You must have heard of it. But what we're interested in is the alloy FESCTE 5050. So what was shown is that somewhere in the vicinity of 50-50, right, there's a range of compositions where you have this band inversion. So not all of this phase diagram is band inverted. Only a range of compositions around this one has band inversion. So please feel free to interrupt me, like I said. So yeah. So this is the band structure. This is the Brillouin zone, and you can see a hole and electron pockets. So let's go here. This is energy. This is momentum. So this is the dispersion, and you can see that right at the gamma point right here, you're expected to have two hole pockets, and at the end point right here, you have a pair of electron pockets that are very similar to each other. So the band inversion occurs between these p orbitals and the d orbitals. So those are the two orbitals that get flipped, and that's how you have band inversion in the system. And so what happens is if you start from one of the ends, then these two bands close and then reopen and then create band inversion. So once you have band inversion, then you expect to see non-trivial surface states. And in fact, that's what they showed in this 2018 work. They showed that this is a bulk band shown in white here. And, maybe the other bulk band is up here. But inside the gap created by this band and this band, you have these linearly dispersing states. And they were able to show that these are indeed surface states. They have Dirac dispersion, and they use spin polarized ARPES to show the spin texture of these surface states. Okay, so now let's go to scanning tunneling microscopy. Bent, how long have I been talking?
It's now 11 o'clock.
And how much time do I have?
Yeah, at least another half an hour. I mean, usually the seminars are 1 hour. It's not too strict, so don't.
Okay, yeah, no, I'm not going to go over. I just lost track of time. Thank you.
Okay.
Okay, so now let's go to scanning tunneling microscopy. I'm sure many of you are familiar with STM, but let me just give you a brief, very quick overview. So it's a very simple technique in principle. In practice, of course, there's a lot of engineering involved, but in principle, you bring a very sharp metallic tip very close to within a few angstroms of the surface that you'd like to study. And you apply a small potential difference, and that causes electrons to tunnel from the tip to the sample or the sample to the tip. And this is the only measurement we make. We measure this tunnel current as a function of bias voltage and also as a function of height, that is this height between the tip and the sample. All the scanning tunneling microscopes in my lab are low temperature systems. So, and they're ultra high vacuum. So there's an STM, it's in ultra high vacuum surrounded by liquid helium. And then the whole thing is mounted on vibration isolation legs. And then finally, it's mounted in the soundproof room, and it's all in the basement to minimize vibrations. So we have 4 different scanning tunneling microscopes, and the one that was used for all the data that I'm going to show you is this one. This is a commercial system made by Unisoku in Japan. This system goes to 300 millikelvin and it has 11 Tesla magnet. Okay, so this is the crystal structure of FeSe or FeSCT. It's a really nice compound because it's layered. So for STM, what we do is we glue a rod to the top of it and simply knock off the rod, thereby revealing a fresh surface. The material cleaves between these 2 layers, and what it reveals really is this selenium plane. So these orange balls. Right underneath is the ion plane, which we really don't have access to with the STM. One thing I would like you to notice is that you have selenium, ion, selenium. Those are the layers. This is one sort of unit cell, if you wish. And the selenium on top and the selenium at the bottom are actually shifted with respect to each other. You can see this better here. So I'm going to point, so for example, these dark orange balls, these are the selenium atoms on the top. These are the iron atoms in the second layer. And then these ones would be the selenium atoms underneath. So when we look with the STM, we can only see these selenium atoms on the top. And the one important thing to notice is that, if you take a certain crystal, pick any crystal you want, then whether the seleniums here are at the bottom or on the top is actually a choice that the crystal makes when it's growing. So you can imagine that there would be lots of areas of the crystal where this is actually flipped. So you'll have domains in the crystal where, in one domain you have seleniums on the top here, but in another domain you might have the seleniums flipped around and going to the bottom. And this is going to be important for what I'll show you later in the talk. So here's an STM topography. You can, if you squint, you can see the atoms, but, we can zoom in. And these are the atoms. Remember, this is an alloy. It's iron, selenium, tellurium. So there's a lot of disorder that you see with your eye. And the reason is that there's a different contrast in STM between the selenium and the tellurium. And in fact, if you look carefully, you realize that this is almost 50-50. So the dark areas and the bright areas occupy 50% of the image, and that's exactly what you want. If you were to take a line cut, meaning you take spectra along this line, so, let's say 100 spectra or so, then this is what you see. First, it's a superconductor, and 0 is the Fermi energy. So you have sort of these two coherence peaks symmetrically placed around the Fermi energy. And I don't show it here. This is 0. So this density of states actually does go to 0. So this is a beautiful S-wave superconductor with basically no density of states whatsoever inside the superconducting gap. But the interesting thing to notice, of course, is that it's extremely inhomogeneous in a few different ways. One is that if you tracked any given gap as a function of position, then its energy actually shifts around a little bit. So you can see this one getting bigger, for example. The other thing that happens is you don't have just one gap, you have multiple gaps. And each of these gaps, as it turns out, represents the gap on the different bands that I showed you earlier. So there's the band at the gamma point, at the M point, and then there are those two hole pockets at the gamma point, and each of them has a slightly different gap size. And therefore, that's what you see in STM as the coexistence of different gaps in real space. So if you do a sort of a survey of the literature and you figure out all the gaps that people have observed, then this is what you come up with. So from specific heat, angle resolved photoemission, optical conductivity, and so on, you have these gap values. The two whole bands, the consensus is, this is an outlier, the consensus is that they have a gap of 1.5 and 2.5 MeV. And the electron band has a much larger gap. And the surface state that I showed you earlier that ARPES has seen, that has a gap of 1.8 MeV. So if you leave aside this gamma band gap, which is much larger, what we should see with STM is 3 low energy gaps, one at 1.5, one at 1.8, which would be the surface state, and one at 2.5 MeV. So how do we figure out what gaps we are seeing? What we do is the following. We take an area like this, which is like—
Quick question. And so this electron gap at 4 MeV, why would I not expect to see that?
Yeah. So no, it's not that we don't expect to see it. We do expect to see it, but the one thing I would point out is that even ARPES sees this. This band it's very broad. The coherence peaks are very broad. And in STM, what we have found is that we do see it, but it's very subdued. So you don't see very sharp coherence peaks associated with this. So it's really hard to keep track of it. And so I'm not going to show you any statistics on this particular gap.
Okay. Mm-hmm.
Okay. So so what we do is we take this field of view and then we measure spectra along a grid. So for example, we might split this up into 256 times 256 and measure spectra along that grid. And once you have all the spectra, we can use a computer program to figure out all the gaps. So that's what we did. And so here's what we usually call a gap map. But here what I'm plotting instead of the actual gap value is regions where we see either one gap or two gaps or three gaps. Okay, so we can, and so now I have all the statistics that I need. So if I pick all the three gap regions, this is what we get. So we have these histograms. This tells you all the gap values that we found in the regions. And you can fit this histogram with these, just a Gaussian distribution, and pick out all the mean values. So here I get a mean value of 1.3 MeV, 1.8 MeV, and 2.4 MeV. So, so now if I can compare to ARPES, so I have the 1.3 millielectron volts and the 2.4 millielectron volts belong to these hole pockets. And the 1.8 MeV, which is also seen in ARPES, is actually the surface state. Okay, so at least we have some indication a priori that.
One more, sorry, Vidya. So, so the 1.8 surface state gap, you see that essentially everywhere, or is that subjected to alloy disorder?
No. The problem, it's very disordered. So you see this, you can see that it's broad. So it's disordered, it's a broad distribution. You can even see just from this histogram that if I went to a region here, for example, that had gaps like this, then the gap on the from the alpha band and the gap from the surface state have the same value, for example. So I would not be able to tell them apart. So there are areas of that's why I wanted to show you this gap map. A lot of the surface has only, we can pick out either one gap where all the gap values are the same, or two gaps where, two of the gaps have merged into one another to give you one coherence peak, or regions where you have three distinct coherence peaks. And for this statistical analysis, we picked only the regions which have three distinct coherence peaks. So if I picked the other two regions with one or two gaps, then so with one, it would just be a big blob, right? With two, we can actually see some structure in that sort of matches this statistics.
Okay, understand. Mm-hmm.
Yeah. Okay. So now let's ask, what do we see when we turn on a magnetic field? What do we expect to see? We expect to see a sharp peak in the density of states if we have Majorana bound states. I'll tell you why in a few minutes, why this is tricky. So what we do is we take a DI-dV map, a density of states map, add the Fermi energy where you expect to see the sharp peak. And of course, you see vortices, right? Because each vortex has states inside the superconducting gap. And so here there is no vortex and it's dark because the density of states is 0. And here you have a sharp peak. And so there's finite density of states. So that shows up as a bright region. So you can, if you look carefully, you can say, oh, look, this is almost a hexagon. So these vortices do form a sort of a disordered lattice. It's disordered because there's a lot of inhomogeneity. So it's not a perfectly hexagonal vortex lattice, but you can sort of see the vortex lattice. And then if you take a line cut, the data that I showed you earlier is actually data from our sample. So if you take a line cut across one of these vortices, you do see this sharp peak in the density of states right at the vortex core. So we were not the first people to do this experiment. In fact, this experiment was done in 2018. And what they showed is that they were able to find these very sharp peaks in the density of states exactly at 0, but only about 30% of the vortices showed these zero bias states. And the other vortices, as it turned out, showed in-gap states, but at different energies. So you might ask the question, what is the proof that these states are actually Majorana bound states? The complication, of course, is that if you turn on a magnetic field and get vortices in any superconductor, then inside the vortex core, you expect to see trivial bound states as well. And we know about these trivial bound states. These are the Cayley-Dejean's metricon bound states. And if you ask at what energy do you expect to see them, you expect to see these Cayley-Metricon-Dejean bound states at an energy approximately given by this quantity here, where delta squared is the gap energy scale, and EF is the Fermi energy of the band that hosts the superconductivity. And mu is for these ordinary bound states, mu is a half integer. So you can ask, what about for this material? Where do you expect to see these Cayley-Dejean metricon bound states? So for us, the gap is around 1.5 MeV. The Fermi energy, as it turns out, for these surface states is around 10 MeV. And so what you expect to see is these Cayley-Dejean metricon bound states at around an energy scale of 100 microelectron volts. So 100 microelectron volts for a low temperature STM, we can actually resolve this. So Hanaguri's group in Japan did a lot of beautiful, careful work with a very low temperature STM, and they showed that within their experimental resolution, they could clearly see that this in-gap state, which is at zero bias, zero, but with some spread, is actually far within the 100 microelectron volts where you expect to see these ordinary Cayley-Dejean metricons. So these are the ordinary bound states, actually. They also showed something really interesting. I told you earlier that only 30% of the vortices showed these zero bias peaks. But what they were able to show is that if you go to very low magnetic fields, like 1 Tesla, then the percentage of the vortices that show you these zero bias peaks actually goes up to almost 80%. So it seems as though as you get to higher and higher vortex densities, these Majorana bound states maybe perhaps interact with one another. I don't know the exact mechanism. And the number of zero bias bound states you see goes up with increasing field. Another beautiful recent experiment is this experiment by Hongding and Hongjun Go, where they showed that for normal Cayley-Metricon-Dejean states, like I said, this mu is a half integer, but theoretical calculations have shown that for Majorana bound states, you expect to have integer spacing, and that's what they see in these special vortices. They show that these bound states inside the vortex core, there's a zero bias one, of course, but then there are others, and they have integer spacing. So all of these this is all a very strong indication that, this kind of a model that predicted zero bias Majorana bound states might actually be working for the system. What we wanted to do was to see if we could detect these kind of propagating Majorana modes along boundaries in this material. So let me just remind you what Fu and Kane predicted is that if you have two areas of superconductivity with some kind of a phase shift between them, pi is ideal because that gives you these two branches of Majorana fermions. Look, these are actually dispersing or propagating Majorana modes. But even if you had some random phase shift, you would still get Majorana bound states, propagating Majorana states inside the superconducting gap. So we decided to look for this. And so what do we need? You need superconductivity. This material is a superconductor. That's not a problem. You need it to be topologically non-trivial. That is true as well, we believe. What about getting a phase shift? How do you engineer areas of the superconductor to have different phase shifts? So these things happen. As it turns out, this is a very nice material. In 2013, Jianping Hu predicted that in this particular kind of material with this kind of crystal structure, meaning the nictide superconductors or the iron-based superconductors, you can show that if you take all kinds of hoppings, nearest neighbor, next nearest neighbor, and so on into consideration, then you can show that in real space, the superconducting order parameter has a phase shift between the top layer and the bottom layer of this, these tri-layers that I was talking about, selenium, iron, selenium. It has a phase shift between the top and the bottom. So if you could find an area of the material where, like I told you, this is flipped, right? You want the top and bottom to be flipped, then perhaps there, right at that boundary, you might have a situation where the two sides of the material actually have a pi phase shift in the superconducting order parameter. So we're looking for structural domain walls in this system. And so a lot of the material looks like this. The material is beautiful, but once in a while, in fact, my postdoc claims he can even see this with his eye when he's going to find these kinds of domains. But once in a while, you have areas of the material where you have a lot of domains. And not all of the domains that we found are those kinds of domains we're interested in. But here, for example, is one such domain wall. This is just a topography. And you can zoom in and, before you zoom in, you can take a Fourier transform. And even in the Fourier transform, you can see that, so these are the lattice peaks in the Fourier transform. If you look closely, you'll see that this pair and this pair, this lattice peak and this lattice peak are actually split into a pair of peaks. And that tells you that in this field of view, you have sort of two domains. Now, it doesn't tell you that they're exactly the domains we're looking for, but it tells you that this field of view has a structural domain, two structural domains separated by a domain wall. You can zoom in and try to track the atoms with your eye, and that's what I'm doing here. So if you go to the left of the domain wall, all these little balls, you track the positions of these atoms. By the time you get to the right of the domain wall, you land up in a dark area, an area between the atoms. You can also do Fourier analysis and show quite clearly that actually this area and this area are shifted from each other by half a unit cell. Okay, so we found domain walls which are shifted by half a unit cell. And now the question is, what does the spectra at these domain walls look like? And this is what it is. So far from the domain wall, you see the beautiful superconducting gap. Here it happens to have two coherence peaks and literally zero density of states inside the gap. And you go to the domain wall, and what you find, and we were very surprised when we saw this the first time, we hadn't thought all this through. What we find is that at the domain wall, you get a finite density of states inside the superconducting gap. But instead of getting peaks, which you would normally do, STM people see a lot of peaks inside the superconducting gap whenever they encounter a defect or a step edge or so on. Here, what you find is a very nice flat density of states. So you can see this more clearly. This is sort of a line cut. First, we go in this direction, and then we go in this direction. This is an intensity plot. So when we go in the bulk of the material away from the domain wall, you see a nice superconducting gap. This is this dark area. And then you can see the coherence peaks lighting up here. And then as you go along the domain wall, you don't see any sharp features. You just see, very nondescript flat density of states that looks like this. So you can do temperature dependence to make sure that this is not some artifact of the domain wall. So here's at 1.7 Kelvin, and here are the two spectra on the domain wall at 1.7 and at 14 Kelvin, where superconductivity is gone, and this feature is gone. But more importantly, the normal state density of states is very similar if you look at the domain wall and far from the domain wall. So this is really a feature of superconductivity in the system. So the question is, what is this? Why do you get this, very flat density of states?
So Vidya?
Yeah. Yes?
So essentially the constant density of states that you observe, that's that's what you're saying is sort of a sign of a linear dispersing band in 1D.
Yeah.
And you see that both in the superconducting and in the normal state.
No, so in the normal
Okay,
state,
thanks.
and sorry about that, I went pretty fast. In the normal state, the band structure is such that near the Fermi energy, I don't see the scale here, but close to the Fermi energy, I think it's the same scale as this. Basically, close to the Fermi energy, the density of states is sort of, there's no features in the density of states. What I really wanted to show you here is not that it's flat, but that the density of states on the domain wall and away from the domain wall are not that dissimilar. They're pretty similar to each other. That's all I wanted to say.
Okay.
Whereas,
so it's not a 1D Dirac state in normal state.
Yeah, exactly. Like you don't have there's no special dispersion or anything like that in the normal state. What happens is in the superconducting state, in most places, you can actually see remnants of the coherence peak, which is actually really important, right? And then you see this finite density of states inside the superconducting gap. And so Ben said it, what is this finite density of states? Why don't you see peaks and so on? You usually, when you have a defect, you should see bound states, but there's no reason for you to see bound states at all energies inside the gap. And the answer is, of course, what you expect to see in the system is you expect to see these helical, by the way, these are helical Majorana states, which have linear dispersion. And if you ask the question, so if you have these linearly dispersing states, so E is proportional to momentum, and in 1D, what is the density of states of these linearly dispersing states? You expect to get constant density of states. And that's what we think we're seeing here. And then we can, of course, do a little more than that. We can take density of states map. And the goal of this is to show you the following. I want to demonstrate that these states span the gap, which they're expected to if they're Majorana states, because that's one of the rules. So these, let me go back here. These linearly dispersing states, they must connect this band with this band. So they're expected to span the gap. And the second important thing is that the spatial extent of these states must grow with energy. So now I'm showing you density of states maps as a function of energy along this domain wall. So at zero bias, right in the middle of the gap, you see states that are pretty nicely confined to the domain wall. But as you go up in energy, what you find is that the spatial, so these are the states at 0.25 MeV, for example, so somewhere here. So these Majorana states, their spatial extent is much bigger. At 0.5 MeV, you have Majorana states with even a larger spatial extent and so on, until finally they span the superconducting gap, even in real space. So this is exactly what you would expect for Majorana states. Okay, that's it. I'm at the end of the talk.
I have a question. In the previous slide, in the panel F,
yes.
So, in panel A to E, we see that the di by dv at the domain wall, that's increasing, but in panel F, it's reversed.
Yeah. Yes. So that's because now you've reached the band edge, right? It's here. You're beginning to see the coherence peaks.
Okay.
So yeah. I mean, this thing is sort of stretched in a very strange way, but that's what it is. You're beginning to see, you're at the tail of the coherence peak. So that's why it's bright. And remember, these things are pretty localized, right? The zero bias ones are pretty localized. Even the 0.25 MeV ones are pretty localized. So by the time you get to these energies, that you're getting dominated by the coherence peaks. Yeah. So these are energy slices. Yeah. Okay.
Thank you.
Yeah, sure. Okay, so that's it. I think all I can tell you is we actually ironically we were extremely skeptical when we first heard that this material was this magic material with band inversion and superconductivity. And also it happens to be an S-wave superconductor, which is also one of the requirements, all in one. And we set out to show that maybe it wasn't, we wanted to show that maybe there weren't any Dirac surface states and so on. And then when the first experiments that we did with the vortex cores were really puzzling, because like the other group had found, we found that just a small portion of the vortices showed these zero bias states. And in fact, most of them didn't, because, we were applying a 5 Tesla field. But as we worked more and more with this material, now there is sort of mounting evidence that these are indeed Majorana states, both these bound states and these propagating states. I would say that the latest vortex core studies done by Hanaguri's group, as well as Hongding and Hongjun Gao's group, are pretty convincing. The fact that they see states localized exactly at zero bias, and the fact that they see integer spacing, I think that's pretty amazing. The linearly dispersing domain wall mode that we observe, I've worked on many different superconductors, and every time there's a defect, a magnetic defect in an S-wave superconductor, for example, will show you a peak in the density of states inside the superconducting gap. I've never really seen such constant density of states filling up the superconducting gap so nicely. It is pretty intriguing. So I think just one thing by itself is not strong evidence, but I think the combined weight of evidence from the vortex core studies as well as this makes me think that maybe we've indeed been able to measure these Majorana states. And that's it. Thank you for your attention.
Yes, thanks, Vidya, for a very exciting talk. That was really interesting. Okay, I asked a few questions throughout, so maybe I'll ask the audience first if there's any questions, either by chat or simply by unmuting your microphone. Okay, if there's no questions, so these are dispersing Majorana modes. Do you see any ways of sort of nucleating bound states along those, say with additional magnetic order, as you indicated earlier when
one thing
I asked related to that subject?
I don't have it here, but one thing we did find is that these domain walls actually sometimes branch out. And what we find is that if you find an intersection of these domain walls, then at the intersection, we see actual zero bias peaks in the density of states. So it looks like there's no theory that I know that shows that you should see bound states at the intersections, but that's what we find in our experiments. So that's an interesting observation. How do you trap these propagating modes and make them localized? I don't know. Remember, they're protected by topology. So in theory, they're supposed to be indestructible unless you destroy the topology of the system. So yeah, I don't know how to turn these particular ones into bound states. Maybe if you had
so I guess that's
magnetic domain, you're right. So let's say you put a magnetic domain on top. So right at the edge of the domain, maybe you will see magnetic, a Majorana bound state. Yeah, it's possible.
Okay. I guess that's one reason why I asked about alloy disorder, because you could, for example, think of the case where you would have regions of your crystal that are not exactly those 40% stoichiometry, in which case you may not have the topological surface state at 1.8 MeV, right? So at the boundary to such a region, I guess it's maybe hard to find them, but
the
that's
problem is, that's a really good question, actually. No, that's a really good question. The problem is that these are not, so this is not a topological superconductor. So in the non-conventional sense, in the following sense, if you truly had a topological superconductor, then at the boundary of the topological superconductor, just like in a topological insulator, you would expect to see, 1D propagating Majorana fermions. But the problem is that for this particular scenario where you have a proximatized topological insulator, only in certain circumstances do you see these propagating modes. So you would not see these propagating modes at the boundary between this superconductor and a trivial superconductor. So that's not the scenario in which you realize these kinds of helical Majorana fermions. The scenario is very strict. You have to have a pi phase shift or some kind of a phase shift in the superconducting order parameter. So it's like it's only an effective P plus IP. It's not actually a topological superconductor. So not all boundaries. There's no constraint that the boundary of the system should show these helical Majorana fermions.
I see, but it does require the topological. I mean, it does require band inversion in the surface state,
in the
right?
bulk of the material. So it's a very strange situation. You start with a topological insulator. It's not a superconductor, and then you proximatize it with a superconductor, and then remember the bulk is S wave. The surface state, the proximity effect is also S wave. What I mean by that is the surface state surface state is fully gapped. So there's no P wave here at all. But you can show that it's effectively, under certain circumstances, it effectively behaves like a P wave. And the circumstances are very special. You turn on a magnetic field in the Vortex cores, it sort of looks like a P wave, a spinless P wave. You have these kinds of phase shifts in the superconducting order parameter, then you can get Majorana, dispersing states. But at the boundaries of the system, you don't get helical Majorana modes.
I see. Mm-hmm.
Yeah.
I have a
yeah. Do we have any more questions from the audience? Maybe.
Bent, can you hear me?
Yes, I can.
Very good. I have a couple of questions, if I may.
Sure. I can't see everyone, so I don't know who's talking. I'm sorry. Maybe I should switch to speaker view.
That's okay. So in your domain walls, they will break translational symmetry.
Not along the domain wall, though.
But across it.
Across it.
Yeah. Which means that you should get an induced odd frequency superconducting component at the domain wall.
But okay. So all I can tell you is that might be true, but there are a couple of things. One is that would not give me constant density of states, right?
It would give you an in-gap, it would give you a non-zero in-gap contribution.
Yeah,
so you
that's right, but not a constant density of states.
Inside the gap. But then you will have broadening. You will have broadening.
Mm-hmm.
And the broadening, because the odd frequency component will be P wave, so it will be smeared considerably by disorder. So I was wondering if you could really distinguish this odd frequency contribution, which must be there, if you could distinguish between your Majorana scenario and this odd frequency scenario in your data.
Would that odd frequency scenario also explain this?
I'm not aware. I would have to think about this. Off the top of my head, I can't say.
Well, that's also an interesting scenario. I'll have to. If you told me, in the odd frequency case, this is what you expect, and in the Majorana, so I don't know how to distinguish between them. I'll have to think about it. Okay. Yeah, I know that usually if you have an odd, if you have an odd frequency superconductor, then the gap, you'll see a gap, and then you're right, it'll be sort of V-shaped gap, right? And then you're saying, hey, you may not have the resolution, you're smearing it out, right?
Yeah. Typically, you will have some in gap states, and the STM data that I've seen so far, they haven't been particularly convincing. They've been mainly on sputtered multilayers, I think. So there's a lot of spatial inhomogeneity, regions where you have what look like subgaps, regions where you have zero bias peaks as well.
Right, right. Yeah, no, I would not know. I would have to ask you or someone else to give me sort of smoking gun, measure this, see if you see that. If you see that, then it's odd frequency, and it's. I'm sorry, I can't.
That's fine. I was just interested because I didn't see a good way, so I wondered if you knew.
The only thing I can say is there is this, right?
Yep.
One has to ask if you can explain this.
Yep.
This is pretty striking. One thing I would say is if you went to this point and you measured DI/dV, you can actually see it in the spectrum. You can see, so these spectra, the completely flat density of states is obviously right in the middle, right?
Yep.
Because that's where you have this and this and this, all the states coexist right in the middle. But if you went slightly off, you can actually see that these states don't exist, and then these will show up as two little bumps.
Yep.
And then when you go slightly even further off, those actually go further out in energy. So you can see all those little details when you look at our spectra. So I don't know, you would have to capture all that in the odd frequency scenario.
The other thing I wanted to ask was, do you have any regions of your sample where you can clearly see a zone which is completely surrounded by domain walls?
You want a little area.
I want an island completely surrounded by domain walls.
We haven't looked for it, but what is the interesting thing about that?
I was wondering how the spectra evolved inside, within the domain wall constituting this island. I was wondering how the spectra evolved as a function of magnetic field. This goes back to the comment one of my colleagues made earlier, where we were talking about the fact that Majoranas always come in pairs.
Yeah.
Now, if you have in the 2D limit, you have to have then obviously you don't have two ends of your vortex. So there, either your vortices come in pairs, or what's also possible is that the Majorana and the vortex can pair, the localized Majorana and the vortex core can pair with the delocalized Majorana in the island state. So I was wondering if you had any small islands, whether you would see any interesting periodicity with magnetic field in the average spectra in your domain walls, which could correspond to different numbers of Majoranas being present inside the inside the walls as a function of magnetic field as you add and remove vortices.
Ah, I see. Wow, that's a tricky experiment, but I see where you're going. Oh, I see. Interesting. Okay, I mean, if, I never imagined we would see this. So
it's already a great start. Yeah, fantastic result.
Yeah, so if we can see this, we might be able to find areas that are completely enclosed. And then I see the experiment you're proposing essentially change the field and ask if there's some sort of correlated change in the vortex,
exactly,
zero bias states and the domain wall states. Yeah, that's a very neat experiment. It would be nice to do.
Okay,
I agree.
Okay, maybe I ask one more question. I think we're almost out of time. So with view on sort of Majorana braiding and logic operations, I mean, it's fairly clear how you would, or it's not what, there's been proposals for braiding Majorana bound states and vortex cores. How would you go about sort of exchanging braiding Majoranas that are dispersing? You
can't. So there are papers that talk about how you could use these, but I did not understand them. It's very complicated. It's not as simple as braiding exchanging
bound state wave functions,
the bound states. No, and So really, our goal is usually to understand the physics, and like I told you, we were trying to ask the question, is this truly this ideal system where you have a surface state, a topologically non-trivial surface state, as well as a superconductor all in one system? So it's not that easy to use these, I think. Also, one has to remember these are helical. So they're not chiral, There are two branches. So I would imagine that if you really wanted to use these Majorana fermions, even the propagating ones, you would be better off having a system with chiral Majorana fermions. So in terms of applications, I'm not sure this is an ideal system.
Oh, I see.
Not these propagating ones, yeah.
What's necessarily the disadvantage of using helical?
So the nice thing about, because they're their own antiparticle, they can annihilate each other, right? So the advantage of using chiral ones is that you have just one branch, and then they're very, very robust. Whereas here, I don't know exactly what impurities and defects would eventually do. Yeah, I don't know, but it's not ideal to have two dispersing branches. You prefer to have one for applications.
Okay, thanks, Vidya. Yeah, so if we don't have any more questions from the audience, so I don't see anything in the chat right now. And we are
stop sharing.
Sorry?
Stop. How do I stop? I don't know how to start. Let's see. Pause sharing. Oh yeah, stop sharing. Okay, there we go.
Okay, thanks, Vidya. That was a very exciting talk. Great work. Yeah, and thanks for sharing your science and joining us for the seminar.
I'm very happy to be here. Like I said, perhaps in person another time.
Hopefully next time. Yeah. Okay. All right. So I wish you a good night.
Thank you.
Let's be in touch.
Yeah, absolutely. Have a great day, everyone. See you later.
Thank you.